Let's talk about Posix threads and synchronization that are available to us in when we do application programming in C on Linux-based systems or Unix-based systems. So one of the things that is that we can take a look at a producer-consumer example using threads. So we will look at very simple example in the beginning. We'll have a producer and consumer. We'll have a multi-threaded program with producer and consumer, and they are basically manipulating a singly linked list. And as you can see, I have in this program, this is a main program, I call pthread create, and I call 3 times I call pthread create, and I create a consumer here, and I create a producer here, and I create a printer here. Now what is a printer? We'll soon see what's going on here. So the printer is going to print the linked list. So it's always printing all the time and in a while one loop, and the producer is also in a while one loop running forever, and it acquires a lock, and then while list total number of elements on the list are less than 10, it keeps adding a new random number in the range min to max in the on the list. So that's pretty clear. And consumer runs in a for loop, forever loop also, and it basically, as long as the total number of elements greater than 0 in the list, it consumes and deletes. There's no condition variable, like there's a mutual exclusion with pthread mutex lock. Only one person can manipulate the list at a time, but there's no signaling going on here. So everybody gets their fair share of threads scheduling, and then they try to acquire the lock, at least producer and consumer, you can see. And here in printer, if you see, the printer also it prints the print list function. It calls print list on the list to print each and every element in a forever loop. Now it obviously, if you see the list.c, the print list function, the list head is null, it returns. Actually it doesn't return, see that. Now it actually prints a message saying the queue is empty. I would say it should have probably returned, because that might be better. Let's say do return here and temp. Otherwise it comes on line number 77. As you can see, it takes a list head and simply a fair straightforward list walking the list function. So as you can see, everything is looking good. We're going to build this program. We will make, there you go, and now we'll run it. Now what happens? We see that this program does a core segmentation for core dump. See, as soon as I run it, it does a core dump. Why? Because printer, you saw the printer function in protcon.c, that guy is not having any protection, any mutual exclusion. Basically he is not worried about if somebody else might be manipulating the list, head pointers, next pointers, anything. List is being manipulated continuously by producers and consumer, but in a mutual exclusion. But printer is, I deliberately commented our pthread mutex lock, and that's causing the crash to happen. Now one thing we'll see is, can we, so now you see, before I change anything, see, core fault, segmentation fault codum. See, now imagine I don't do that. I run this command using task set. If you don't know, the task set is a command on Linux that lets you run a process on a specific CPU rather than its threads running all over the place. They will be the process, and all the threads of the process will run only on the CPU, or the range of CPU. In this case, I am giving only one, because on this machine there are two. So two. Okay, let's see what happened. Okay, it actually crashed even with task set C1. So sometimes you see it doesn't crash that fast, which is surprising. But what is going on, that with task set it doesn't right away crash. The reason being that if all the threads are running on the same CPU, then if they are serialized, then the chance of this hitting into this corruption of the list, because printer thread doesn't have mutual exclusion, becomes low, because the it doesn't have the mutual exclusion. It's not calling pthread mutex lock. See, now it's running a long time, it's not crashing. What's going on here? So what we are going to do now is we are going to go back to the protcon.c, and we'll go to the printer function, okay, here, and we're going to actually have this pthread mutex lock lines back. See that? Now you see that we don't have to do a task set or anything. If you do a make, there you go. And now if you do a protcon, obviously it doesn't crash. So you just saw how the pthread mutex lock is used to protect the critical section. So this is here, the critical section is manipulating the list, adding to it, consuming from it, printing it. That whole thing is critical section. So that's your critical section, right? So that's why now you see there's no crash. I don't even have to do a task set. Task set is not even required. But if you were to go back there and remove that uh, mutex lock in pthread, here you see the crash will again start happening, because you're not protecting the critical section. So you see now, as soon as I run the program, it will crash within a minute. See, look at that. It doesn't even take a minute, less than a minute for it to crash. See, there you go. So now if you do a task set, it still crashes, but sometimes you see with task set it keeps running for a long time. Why? Because when you have all the three threads running on the same CPU, and they are the if you would think kernel is preemptive, they are basically being preempted when their time slice is over, right? They won't run forever. These are user threads, so they can't hog the CPU. Well, by the way, in Linux, even kernel can be preemptive if you set it up that way. So even a thread in kernel space, completely in kernel space, can also be preempted. So not just the user threads, but even the kernel threads can get preemptive. So in this case, you would think that whether it is task set or not, the crash is inevitable after some time, even though with task set the crash becomes less likely. Why? It seems that when you have those threads are forced to run only on one CPU, considering that consumer and producer are still being mutually exclusive, only thread that's a problem right now is the printer thread, which doesn't have the pthread mutex. So anyway, we will not play with this task set, but it's good to know that there is a command on Linux which can force a process to run only on a particular CPU, and it's good for, you might ask what it is good for, and it's good for like for example, if you want to increase the performance of a process, because it doesn't. Maybe you want it to have less cache misses. When the process always running on the same CPU, it's likely to find its data in the cache more often, right? So that's the reason why people have this CPU affinity thing in Linux, where you can actually specify by a bunch of system calls or this command that I mentioned, task set, to run the program on a particular CPU. Now you see I put the locks back in printer. You don't need task set or anything, you just continue. It doesn't matter where those threads are running, it's happening, it's good, life is good, and everything is fine. Now let's introduce, we just introduced pthread mutex lock. Now let's introduce condition variables and why do I need it. Now you see in the mutual exclusion what happened is that you only had the mutual exclusion, but there was nothing like, hey, I'll go to sleep, wake me up when things are ready for me. And for with that, this that paradigm in pthread Posix threads can be implemented using condition variables. So let me explain to you pthread mutex type. So we still have a mutex like last time, which is the same, but now we have two condition variables corresponding to two threads, producer and consumer. And I guess these are signaling mechanisms. So what happens is that thread A will signal on the other condition variables. So that's how it will work. Each thread signals on to the thread. So I don't want to confuse you, but if you see here, see, go to, let's look at the producer here. Producer is thread A. The thread A runs in forever. What is the first thing it does? It protects the predicate. They call it predicate, the lock. Need a lock to protect the predicate, flag lock. So here you see it does a mutual exclusion. It takes the lock, and then it and then this flag is there. See this flag? This flag lock was there to protect flag. This flag is the predicate. So that is kind of way to for them to signal each other. They say, hey, now you go ahead. Then the other guy says, now you go ahead. So you see, while flag, it does a convert on this producer condition variable here, and second argument is the flag lock. So this is a quite complicated stuff here in pthread convert. In the sense, what it does is it does a atomic. There's something atomicity going on here. So it does a atomic lock and wait, and when it comes out of this, you have the lock again. That is why you see here I'm doing a mutex unlock on flag lock. So the reason why you pass the flag lock as a second argument, lock mutex lock as a second argument to convert is because it atomically releases the lock and goes to sleep. You can't have something like, if you think that, hey, is it really atomic? No, it is absolutely atomic, and the reason being that so if you ask somebody, if somebody says, okay, so if you really, hey, how atomic it is. So an operation either is atomic or it is not. There are no shades of gray, right? If there is a window in which the waiting thread could miss the signal, no matter how small, then the unlock and wait step would not be atomic. So pthread convert atomically releases mutex and cause the calling thread to block on the condition variable, right? So it releases this flag lock, so that why, and it basically blocks here. Because if it doesn't release, then think about the other guy who's supposed to signal it, it can't go ahead and later on here in the end do a const signal. See here the const wait is not enough. This is all, see, in every thread you see in this producer and consumer there's a const wait and const signal, and const signal happens on the other thread. So const wait happens on thread A. If thread A, then the const signal is happening on thread B, because you want the other thread. Other thread does the opposite of it, does a const wait on thread A and const signal on thread B. So very important stuff to here to understand here, that you basically have const wait, this const signal in a they go together. If you're doing a const wait on a particular condition variable, then you're doing a const signal on the other condition variable, and this thing can be seen in both the threads. So that's, I want to show you, this is an example of two threads only, and there's a producer and consumer, and what they do is they have a what is the producer and consumer part. So here you see there is a buffer here, buffer is of buff size, and producer does the it picks up it pulls a random number here, see, and then it says if buff I, you see, I equal to I mod 10, if I equal to I plus 1 and then mod buff size, it does this. So that basically from buff size being in this case I think it is 10 or something, 10, yeah. So they're basically he's continuously writing, the producer is continuously writing in the buff in a kind of like producing, and consumer is reading from the buffer, see, it reads from the buffer, it sets it back to 0, buffer I to 0, and I equal to, and then he increments his I. So index for his index for the buffer. So that's why how they're going. Remember these beautiful things, that you need one mutex to have mutual exclusion and two condition variables to signal each other, so that you make sure that only one guy at a time manipulates this buffer. Now, so we saw p thread const wait combo and const signal, maybe const wait const signal. So we saw p thread mutex lock, const wait, const signal, three different function calls to a weighted mutual exclusion, kind of mutual exclusion with signaling mechanism, that is p thread mutex lock, const wait, const signal. Now we'll go to the third case where we would have a new kind of, so right now what we saw is, so far we are actually doing what is known as, we are locking the code, in the sense not actually locking the code. Well, let me just say we are actually kind of protecting the code. The critical section is in the code, but there is a saying, and this is a very good saying in software, that you should lock data, not code. So I'll show you what that means. So we'll see one example here. What we will do is we'll have a queue. Let's look at this data structure q1.h. So in this case, instead of simple like buffer of size 10, we actually have a queue, and in the queue we store stuff, and this is opaque. A queue will store opaque types, so that's why it's a void star star. This is array is going to be a dynamically allocated array, and this front, rear, size, capacity, these are queues metadata to manage the queue. But what is important is to understand this array, which will be allocated at the runtime when the queue init is called, initialize the queue. See, and then we have functions like enqueue takes queue pointer. They all take queue pointers, except that enqueue also takes an item to queue on the queue. Otherwise, and they all work on void star. See, so we don't even know what kind of stuff you are storing in the queue. It could be anything. Let's take one example here. So q1.c is the implementation. So you see create queue. This function is you can create a queue with a size of whatever size you want, unsigned capacity, say unsigned int, and it returns a q star. It initializes capacity front to q size, q rear is capacity minus 1. So q front and q rear are the indices on the beginning and the end of the queue, and q size says how many elements you got now. Q array is set to malloc times q star size of star q array. You see, this is the beauty here, is that you are allocating all these pointers, actually void stars. Not the It is not an integer array, it's a pointer of void stars. And so we have these other API is full. If q size equal to q capacity, then it's full. If q is empty, if q size is 0. And function to add an item to the queue, in queue. So in queue is q void star item q rear equal to q rear plus 1 mod q capacity. So that's another beauty here, that keep increasing the uh, q rear pointer mod subject to the mod of q capacity. But I thought we didn't initialize q rear to 0, did we? Because it seems to me that okay, so I can see that enqueue is enqueuing it at the end of the queue. I mean, there are two markers, kind of front and rear. But I thought in the queue create, did we set queue rear also to? Actually, we set it to capacity minus 1. So we are actually putting it in the end. Okay, I see your point. So that means that it is it is always enqueuing at rear. Now dequeue is very simple. It dequeues from the front, by the way. Q front equal to q front plus 1 mod q capacity. So dequeuing happens from the index front, and the enqueuing happens from the index rear. See, this is interesting. We don't manipulate front and rear at the same time. Enqueue only manipulates rear, in and dequeue only manipulates front. So basically it dequeues from the front. Now, okay, so after having shown that to you, let's look at threads based conprod.2.c. You see, what we did in this case is, just to give you an example or show you how beautiful this queue implementation was, that we're gonna do a same thing, like we have a flag, right? And we have a flag lock, need a lock to protect the predicate. We still have two condition variables, but instead of putting just integers, we actually put this prototype structure in the queue. So you see now, and then basically I tried to simulate, imagine the packets coming in, and depending upon IP, ARP, their type of the packet that comes in, you call the handler. So you see what is happening here. Hash function and mod hash function add protocol to queue. So here you see add protocol to queue is going to do enqueue. See, yes, it did. So you say queue equal to get queue. Queue is global. Get queue, okay. And then say enqueue new. What is new? New is a proto star malloc size new type to handler this. And enqueue queue new. So now queue doesn't even know what is being enqueued on it. What kind of data is. So imagine you know that it was just a void star. So it doesn't even know that, hey, you were doing you gave me void star. So that's why I like that queue implementation. It basically very generic in terms of what kind of data you are storing in the queue. And dequeue, you see, it actually typecast is the front queue, and dequeue is queue and return time. And so that's your display stats is another, I think, thread. So producer, let's see what it does. It takes a lock. It uses the predicate to do a while loop, to basically wait. Cond wait happens in a while loop, because even after you come back here, you still have to go to make sure that, hey, did we do a spurious wake up, or like, is it okay? So see, cond wait releases so flag lock and goes atomically releases the lock and blocks on this condition variable thread icon. While you see the consumer is going to do a con signal on thread icon, you can see in the end, so that guy can wake up, can come back from sleep. So you saw another example of the mutex lock con wake con signal, this pairs in but with a queue implementation. So I hope I gave you some ideas on how to do um, p-threads based uh, serialization synchronization in programs where multiple threads are happening, how to protect locked data, or basically serialize access to data shared with global data shared with multiple threads. So this that we saw. Another thing is, some people say that, hey, why you doing that? You should not be locking code, you should not be making code, but you should actually put the data. You should put. So here, this is another implementation before I do a sign off. In this implementation, what you see the queue, we put those three things that were global, mutex and condition variables, inside the queue. You see, now what happens here? Okay, and then we created producer and consumer. Okay, producer, what it does, mutex lock. Okay, FIFO queue. So only difference is that your mutexes condition variables, they are no longer global variables, they are inside the queue data structures. So this is the paradigm of locking the data, not the code. So this is everything is happening inside. So those three synchronization primitives are actually inside the queue itself. So that this is good to keep in mind, actually, because this is kind of a, this is recommended practice in multi-threaded design, to lock data, not code. And I hope with this I can sign off for today and let you guys ponder the implications of p-thread mutexes and conwaits and con signal. And never forget that you need a predicate in all of that. So the predicate will go inside the application program. You see here, application program here, we did a, so if you go to producer, you see it actually has a for loop this time, for I equal to 0, I less than loop, while, and the predicate in this case becomes FIFO full. So if you see, go back there, FIFO full, I think full in this case is int full. This is actually the predicate now in this case. So they're both making sure that that variable is not changed out of, see, FIFO full, and this guy is doing the wait and lock on FIFO empty. So actually you got two predicates in this case, FIFO full and empty. And this guy says while FIFO empty, keep being there unless the producer comes and puts a new item on the queue. It does a count wait unless, and then when it's woken up, because that guy, he signaled him saying FIFO not empty, count signal. So that is why here he came out here, this count wait, and he found out that FIFO empty is no longer obviously will not be true because you manipulated the queue, right? He put a new stuff on the queue, mutex queue add. So did a queue add, when you did a queue add, what you saw is that this he actually manipulated this queue tail and queue full here. See, queue full, and so that's actually, in this case, in a way, if you think about it, we got two uh, predicates. You got FIFO empty and the queue empty and queue full, and they are kind of being protected using this mutex, and conduits are there to signal each other, to kind of one of them to go while the other keeps, only one person at a time can do a queue add or queue delete. Alright, so I hope it was clear, and you will become very soon an expert in Posix Threads programming and mutual exclusion and synchronization and conduits and consignals. And with those thoughts, I will say take care, bye bye.